Computer. Yep, we're good.
All right, perfect. And then Danielle, it's in breakout room.
Hey everybody, sorry for the technical difficulties. Okay, so we're recording now. So the questions being asked, if you voice them, I don't think the chat appears in the recording, if I remember correctly. So I will try to read the questions as they come up. Somebody asked me, can you share the question, or where can I find the question? So the questions that we're doing are either the homework or the recitation. I have stated here in the top part of the problem what it is. So 420 recitation. All of this material is on Walter's website. So go to his website, find today's recitation, and look at problem 2. I'm also describing the problem, but there are details in the problem that are worth looking at yourselves. Okay, so you have a spring and it's compressed, a distance d, they tell you. And they want to find the velocity when you're going over the equilibrium point. So the first thing I want to ask you is, what is true about this system when you're going through the equilibrium point? What does that even mean? Can somebody tell me that? Not everybody all at once, though. Delta x is 0. This is true, because delta x is just a measure of how far away you are from the equilibrium point. So if you're at the equilibrium point, then your delta x is 0. And yes, Cassie, Laura, Cassie, you're correct. At the equilibrium point, the spring is not compressed or stretched. And what that means is that there's no potential energy. If you have a spring or a slinky or something that has elasticity to it, at the equilibrium point, it doesn't want to do anything. It wants to stay there. The only way that you get the spring to either move away from the equilibrium point is by applying a force. So in this case, something or someone applied a force here to bring the spring here. Oh, I forgot to draw that. There should be like a mass attached to this picture here. So when it's saying that, what is the velocity at the equilibrium point, what that really means is that the spring potential energy or elastic potential energy is 0 at that point. Okay. So this is going to be a conservation of momentum, conservation of energy problem. What does that mean? That means that I'm going to take one point in time and another point in time, and I'm going to equate their energies. So I will say at the beginning, well, the beginning is when the spring is here, right? Does the spring have any kinetic energy when it's compressed to this point?
No.
Right. So there's no kinetic energy. Is there any potential energy? Is there any gravitational potential energy in this problem? So kinetic energy, initial equals 0 plus potential energy of gravity. Is there gravitational potential energy in this problem? It's a good question. Somebody says maybe yes. Some people are saying no. There is no gravitational potential energy in this problem, right? And why is that? The spring is not moving up or down, right? The spring is moving side to side. We know gravitational potential energy to be mgh, meaning gravity does work up or down. The spring is moving left and right, gravity acts in the y direction. So if gravity is in the y direction, motion's in the x, the angle between them is 0, work done is 0, okay? So this is 0. So the only source of energy in the system at the beginning is the spring potential energy. Sometimes I write PES, sometimes I write PEL for elastic, same thing. And we know that that is defined as 1/2 kx squared. Makes sense? Or actually, I shouldn't call it x, I should call it d, because that's how much the spring is compressed away from equilibrium. Okay with everybody? Now, I said this is a conservation of momentum problem. So there's some initial energy and there's some final energy. However, um, there is a non-conservative force. And do we know what that word means at all by any chance? Have we talked about what a non-conservative force does in a system? Good. So a non-conservative force means you're taking away energy from the system, right? So there is some work done. There should be like a work term here. And is that work positive or negative in the case of friction? It's negative, right? Because when you release the mass, it's going to move to the right, and the direction of friction is going to be to the left, right? So the work done by friction is negative. So essentially, if I have some, like if I have some amount of energy contained in the spring, by the time I get here, I will have lost some work, some energy due to the work of friction. So that's nice. And then I also have to define, actually, let's define that work before anything. The work done by friction. How do we define the work done by friction here? And yes, Jacob, the potential energy of a spring is always going to be, potential energy of a spring is 1/2 kx squared, where x is how far away you are from the equilibrium position. That's always the spring potential energy. Right, so the work done by friction is the force of friction times the coefficient times the displacement, right? So in this case, the displacement is d. But how do we define the force by the done by friction here? We can define that better, right? The force of friction is going to be mu k mg d, right? Good, exactly. That's exactly right. So now we've defined, so I said that, we have three terms here. We have the initial energy, the work, and the final energy. Now let's consider what happens when the spring is here. So let's draw this picture again now. Now the spring lines up with the equilibrium position. So this is the x equals 0, if you will, right? What is so we know, again, there's no potential energy due to gravity. Is there potential energy due to the spring? Why do we say that there's potential energy due to the spring at the equilibrium point? Remember.
Oh, wait, there wouldn't be any, right? Because it's at equilibrium.
Exactly. That's what I led this conversation with. What does it mean to be at equilibrium, right? Or I wrote to go over, but I meant, to be at the equilibrium point. That means that at this point, the spring is not compressed or stretched. And if the spring is not compressed or stretched, then there is no potential energy due to the spring. Is there any kinetic energy? No, Jacob. The question is specifically saying, how fast will the mass be traveling at the equilibrium point? That is specifically what the question is saying. Jacob asked, isn't it going past the equilibrium point? And again, the reason I'm reading back your questions is because in the recording, you can't see the chat. At least I don't think so. So I'm just going to read back what some people say if it's relevant to the conversation. Somebody said, isn't it past the equilibrium point? No, the question is, how fast will the mass be traveling at the equilibrium point? So I want to know specifically, when the mass goes from d to 0, what is the velocity? And as Jillian said, there is kinetic energy. And that kinetic energy, so the energy final, potential energy of spring equals 0. Of course, there's no gravitational energy, plus Ke final. So I'm going to take 1, 2, and 3 and put it all together. So the initial energy, so let's put this all together, maybe in a different color or something. The initial energy is 1/2 kd squared minus the work done by friction. So we defined 1, 2, 3. The work done by friction is minus mu k mg d equals 1/2 mv squared. And typically we would call that v final or something like that. But since there's only one velocity term here, it doesn't really matter. So now if we want to solve for v, well, that's just algebra, right? That's literally just going to be k d squared minus 2 mu k mgd divided by m equals v squared. So take the square root. So that's the expression for the velocity. Obviously, k is just a number, distance is a number. A lot of the times we're not given what these values are. We just need to solve for it symbolically. Here, mass is going to cancel. So you're just left with this equation. Not too bad, right? All we had to do was define the energy here, and consider whether there's work done in the system or not. If there's a non-conservative force, then there's work. Cool. Any questions about anything that we've done? Even if it seems like a silly question, no question is too silly or too small, because that's the whole point of this thing. I'm not here to teach the problems to the people that already know how to do it. I'm here to make sure that the people that don't know how to do it know how to do it. So somebody asked, where does the 1/2 mv squared comes from? It comes from the fact that in order to use conservation of energy, we need to consider the energy of the system at an initial point and at a final point. And at this, the initial point is when it's compressed. The final point is when it's going over the equilibrium position. So when it's going over the equilibrium position, we're saying, okay, what kind of energy is there? Is there potential energy? No. Is there elastic potential energy? No. Is there kinetic energy? Yes, because it's moving. And that kinetic energy is defined as 1/2 mv squared. So kinetic energy of something that's moving is given by 1/2 mv squared. So that's where that comes from. Hope that helps. Why is there KE at equilibrium? Okay. What's the difference between the m and the m in the final equation? The m, the big M and the little m. I think I just used little m, didn't I? So somebody asked me what's the difference between the big M and the little m in the final equation, but I thought I had just used one m.
They're probably talking about mu.
Oh, this here? Yeah. This is the work done by friction, right? So the question, somebody else also asked, why is the work negative again? Remember, the work is force times displacement, right? Times cosine of theta. If we're looking at an object that's moving to the right this way, we know that friction is going to be pointing to the left. So the angle from here to here is 180 degrees. So work is force times displacement times cosine of 180, which is a -1, right? But better yet, if the force and the direction are in opposite motions, it's negative work. That's one way of thinking of it, physically speaking. This is a way of thinking of it mathematically. Yeah, this mu k is given to you in the problem. That's not an m. Hadar, I didn't understand your question. You said it is passing through equilibrium. Oh, I think you were answering Kelly's question. Why is there kinetic energy at equilibrium? That's a good question, Kelly. Why is there ever kinetic energy in any situation? How do we define whether there's kinetic energy in the system or not? Exactly. And is the stuff moving when it's going through the equilibrium point? It is. So it must have kinetic energy. Okay, so good. I think there was something else. Oh, why is the force of friction equals to mg? The force of friction is not equals to mg. The force of friction is mu k times the normal force. But let's think about this box. This is where physics kind of blends. And even though we're not doing really forces anymore, you're kind of supposed to have some knowledge of how this works. If we think about a box sitting here and we ask ourselves, what are the forces acting on this box? Well, you're going to have the force of friction to the left, right? You're going to have the force of the spring to the right. you're gonna have gravity down, so Fg, force of friction, force of spring, force of normal force. So if we say, you know, the sum of the forces in the y direction, well, there's Fn minus mg because they're in opposite directions, and there's no acceleration in the y direction, so the may has to be 0. So then Fn is just mg. So then the force of friction is mu k mg. If this was on, say, a ramp, it would be mu k mg cosine theta, because that would be the component of gravity that is equivalent to the normal force. There are no such things as bad questions here. I said it earlier and I'll say it again. I'm not here to teach everybody who already knows the problem how to solve the problem again. I'm here so that people that aren't sure why the force of friction equals mg, for them to know, right? That's the whole point of this review. And you know, I think we have plenty of time to go over, you know, big questions or small questions. So don't hesitate to ask the question, even if you feel like it's silly. Yeah, Ryan, this is review problem number 2 from today's recitation. So at this point, we've answered question A, which is how fast it's going when it's crossing the equilibrium point, right? Again, you can think of the equilibrium point as crossing, you know, like the finish line or something. How fast were you going as you went through the finish line? And that finish line meaning you have no potential energy. Okay, question B, if there are no questions regarding A. I think B just wants you to write an expression for friction, right? For the work done by friction as it goes from the initial position to the right of the equilibrium. So now the block, oh, well, that's not how you do that. The block started here, right? This is the equilibrium point. And it ends in the picture, you know, by it ends, it means we're choosing to look at this next part of the picture. Now the spring is here. And this is the equilibrium point. So remember, this distance here is d, and this distance here is df. So the total distance from this point to this point is d plus f, right? Does that make sense to everybody? And yes, that's exactly right. You're going from work done by friction is just the force times the displacement, right? Times cosine of theta. Well, we know the cosine of theta just gives us a minus, right? YF, that's just what the problem called that distance. You could have called it D1, D2, could have called it X1, X2. That's just what they called it. So the work done by friction is going to be, it's not DF, it's going to be the work done from here all the way. So, you know, before it used to be here, right? So it's this distance plus that distance. So it's going to be mu k mg, and the displacement is d plus df. All right? And just to be clear, let me draw it one more time. Oops, sorry, not like that. We want to know how much work friction does if the box moves from, or the mass moves from here all the way to here. All right? So this is df and this is d. Clearly the distance of this is the sum of d and df, right? Because we're going from here to here, from here to here. So the work done by friction is just that. And then, you know, slap a minus sign in front of all this. Any questions about that? Why cosine theta? Good question. So technically the work done, the definition of work is actually the dot product of two vectors. So let's just call this x as an x vector, not x, the x coordinate. And the way that you do this, there's two definitions for the dot product that we use. One of them is fx. So let me actually use the letter s here to not confuse the x's. Let's use s. It's going to be fx times sx plus fy times sy plus fz times sz. And that's going to give you some number. The other definition of the dot product is the magnitude of f times the magnitude of s times the cosine of the angle between them. Remember, these are two really, we're saying that work is force times displacement, but force is a vector and displacement is also a vector. So realistically, you can't just nilly-willy take the product of their magnitude and multiply them. The same way that if you had a vector, being 7 at 17 degrees with respect to the x-axis and, 8 with negative 30 degrees with respect to the positive x-axis, you can't just take those numbers and add them. It's the same thing here. You can't just take those numbers and multiply them. There's a directional component that comes to it, right? So like if I had, let me actually draw this here. It might be a little bit off topic, but it's kind of important. If I had a vector that was like in this direction, it was 7 with 13 degrees, and then I have this other vector that was 7 with 120 degrees, right? Or something like that. And with an angle, let's call this 3. If I wanted to add 7, if I wanted to add the two vectors, I can't just do 7 plus 3 is 10, right? You would say, oh, well, I need to get the components of this vector, the x and the y, and I need to get the components of this vector, the x and the y, add them up, and now I have two new components for a whole new vector that's probably going to be around here, right? Because this vector is much bigger, man. It's going to be somewhere around here. The same, but if you maybe had a vector that looks, you had two vectors that look like this. You've got one in this direction of 5 and one in this direction of 3. Then you can just add the 3 and the 5 because they're one-dimensional vectors. They're pointing in the same direction. Then yeah, you could say that the result is a vector, 2 in the right direction. So you could say that it's a vector like this, 2. But the same logic applies to work. I can't just ignore the direction when I multiply two vectors. The only time I can do that is when the force points in the same direction or in opposite directions. Okay, so that's why sometimes we write just this part. We only really write this part when we're talking about, for example, kinetic energy. Force of friction. Force of friction is pointing to the left, directions to the right. So they're both along the x-axis. But if the force was at some angle with respect to the direction of motion, then you have to have this cosine of theta. Anyway, sorry for kind of getting off on a tangent here, but it is kind of important that we understand that.
So that's why it's just like the nu k mg and then d plus df, and there's no like anything after that. Like we just dropped the cosine.
Right, and technically we didn't drop the cosine. The cosine exists, but remember it's cosine of 180, which is just -1. And if
Oh, I understand. Yeah.
And if they were in the same direction, it would be cosine of 0, which is 1. So, here, sometimes we're just kind of dropping this cosine, but it just means that it's 1 or -1. But again, the same way that you wouldn't add two vectors without accounting for a direction, sometimes you can't just multiply two vectors without accounting for direction. That's only really possible when they're parallel or anti-parallel. So I hope that helped at least one or two people here. Hadar had a question. Does the change in kinetic energy always equal work done by non-conservative forces? Can I always use this equation? Are you saying, can you always say that a change in kinetic energy is equal to the work done by a non-conservative force? No, but you can say that for a conservative force. Wait, can you hold up? Let me think about that. Let me think about this and get back to you because I'm trying to think of counter examples, but I'd rather think about that and get back to you. So moving on with this question. I think there's a part C, right? Yeah, so now it says write down an equation in terms of mu k d mg that will let you solve for the distance df. So now if we wanted, we wanted to know how much work friction did going from here to here. Now we want to find out what that distance d is, right? So we just use, again, conservation of energy, right? So now we get a nice pretty choice here. There are 3 points of relevance in this problem, right? There's the initial point, which is where the box starts. That's useful because we know that at this point, we only have elastic potential energy. Then there's the point where it crosses the equilibrium point here. And this is useful because we know that there's no potential energy here and there's only kinetic energy here. And as a matter of fact, we know what the velocity is already. We solved for it. So we also know the total energy here. So we know the total energy here. We also know the total energy at the beginning. The third point of interest is when it gets to this distance df. Thank you for answering, Cassie. The other point of interest is for this distance df. So if we're going to set up a conservation of energy problem, it's the same approach, except now our E initial and our E final changes from what we did in part A. But we get a choice of what our initial is because we know our initial at 2 other points. So we can choose one. So which one do we want to use? Do we want to use the middle one or do we want to use the initial? Leo, we'll get to that in a bit. Sorry, somebody was going to say something?
Wouldn't the middle one be the easiest?
It could be. I would argue that it isn't because the velocity is such an ugly term. But in theory, this is just a number, right? Like if I had all of these numbers, I'm just going to get a number like 13 meters per second or 7 meters per second or something like that. You could use this, absolutely. And as a matter of fact, you can't set this up and just say, oh, it's 1/2 mv squared. V is a really ugly equation, but I know it. I know an equation for it, so it doesn't matter, so I'm going to use it. That's totally fine. That's more than fine. I would use the initial position because that's just 1/2 kd squared. And I know d is more simple to write than v. Both are completely acceptable. And since you suggested using the middle point, we'll use that. We'll say that initially, there's only kinetic energy, which is given by 1/2 mv squared. And we're not going to plug in what v is because it's pretty ugly, but you could do that later on, right? And the final is when you're here. So question, when you're all the way to the right, is there going to be kinetic energy? No, right? Good. So this is going to be plus the spring potential energy, right? Which is just 1/2 kdf squared. Hold on, something's missing here. Did I make this too easy? Oh, yeah, I know what it is. So now we can say EI, again, we have to subtract the work done by friction here, right? Cool. So then this equation becomes 1/2 mv squared minus mu k mg. The work now done is only from the equilibrium point to df, so now it's just df, right? Because we started at the equilibrium point. That's a, sorry, that was confusing. That's an E, I mean an S. Equals 1/2 k df squared. Cool, now we can solve for df, right? So technically you can't solve for it yet until you plug in what V is, because V has a D in it, and it's pretty ugly. But this is just the gist of it, right? Like this is exactly what you do. You plug that in, and then you can solve for DF. Now this is gonna be kind of an ugly equation no matter how you do it, because even if you leave this in terms of V, if I wanted to solve for DF, I have a DF squared term, and I have a linear DF term, and I have a constant, right? So this is like an X squared, this is an X, and this is a constant. So this is essentially as if I had a quadratic equation, right? And nobody likes to solve those. They're pretty ugly. In general, the only time we have you solve those is when they're nice and pretty ones. Hardly ever will you have to work with something that's like super ugly. If you do, chances are you may have done something wrong, or Walter was just feeling really cruel that day, but I doubt it. But yeah, this is pretty much how you set up the problem, right? Pretty simple stuff. And this is what I've been telling some of my students as I've talked to them. Nothing in this problem is complicated. But if you don't know how to define the energy at specific points, and you don't know the nuances of whether work is positive or negative, then this crap's gonna seem like hell. But really all I did is I defined the energy here. Oh, it was just 1/2 mv squared. Oh, it was just 1/2 kdf squared. Oh, right, there's also the work done by friction, which is just mu k mgd. Put it all together. And it's not a lot of work in my opinion. Now, yeah, maybe solving for df is a lot of work, but you don't even have to do that. You just have to set this up and say, oh, this is a quadratic equation. I'm not going to solve it. Okay. Is everybody okay with this? Are there any questions about the work done by friction here? Any questions about the initial and final energy?
I have a question. If you started from the other side, like when you started with the spring, would you start with the potential energy of the spring minus the force of friction equals like the energy final?
Yes, and there's one more difference. What's that difference going to be?
Is it the friction from D, or like D plus df for its distance?
For what?
Would your like friction force be negative mu k mg D plus df?
Correct. The work done by friction would not be mu k mg df. It would be mu k mg df plus d, because now you're going from the initial all the way at the left to the final on the right. Okay, good question. Any other questions before we move on to the other recitation problem here, which is number 1? Okay, so we're gonna do 428 recitation Q1. Give me a second while I let my dog in. Okay. I don't know when we'll end. We'll probably go for, till 8:30 or 9, depending. I'll try to get to most people's questions. We can't get through everything, but we'll try to get through as much as possible. Okay, so question 1 of the recitation. This is a relatively simple problem. You have like a cylinder here, and attached to it are these 2 discs, right? And they tell you the discs have radius of 10 centimeters, and the cylinder has a radius, let's call this RC of 2 centimeters. And it's like going down on some thing, right? It's like rolling down. And the question says, what is the relationship between the spool's translational velocity v and its angular velocity omega? Remember that if you use variables here, you must tell me their physical values. So I know somebody said something on the chat about this. Would the answer be V equals omega? V equals omega R. And then just to confirm, is the V in the DF equation the V we calculated from A? Yes, yes, it is. Appreciate it. It is the V that we calculated in A. So somebody said, Arda, you said for recitation 1A, would the answer be V equals omega R? Now I'll tell you, yes, that is the answer. However, you need to tell me what each of the terms mean. What is this? What is this? And what is this? What is the physical significance of that? Or anybody, of course, can answer this question. R is the radius of the cylinder. Good. What is omega? Is the angular velocity and linear velocity, right? Why is R the radius of the cylinder and not the disk?
Because the cylinder is what's making contact with like the slope thing,
Correct,
and
right?
the discs aren't.
Correct. So we can imagine that something's rolling on it like this, right? Then this is the R that's, going around. Okay, everybody's on the same page about that? And then, the discs are not making contact. So they're not spinning with respect to the thing. Okay. That's easy. So then question B says, what is the speed, right? When it's done rolling. So I'll redraw the picture here.
Wait, so the answer to number 1A was just V equals omega or V equals omega R and just explaining each one?
No, the answer, yes, exactly. The answer is V equals omega R, and tell me what V is, tell me what omega is, and tell me what R is, and justify it. So now for A, you have to find, I don't know how I made that into a line. So, now I'm gonna go back to drawing boxes. Even though we know this thing is turning, I'm just gonna draw like this. It's going down, right? Some thing that's making a 30-degree angle here, I think. The question is, what is the velocity when it reaches this point? Right, so it's gonna go down this way. What is the velocity when it reaches that point? So who can help me set this up here? What's the approach that we're gonna take here? Somebody says potential energy equals KE translational plus KE rotational. Now that would be correct. The approach here would be to say, okay, we're going to use conservation of energy here and say the cylinder and the disk system has some energy while it's up here, and it has some energy that when it's down here, and those two quantities should be equal to each other because friction does no work on the cylinder, right? So how do we define PE? So this is E initial equals E final. So how do we define the PEG, or the gravitational potential energy? It's just mgh, right? Where I guess this is the height h. or mg, right, same difference. So if this is a length d, oops, if this length here were d, and that's 30, then this would be mg d sine 30. I'm just gonna call it h though for simplicity, especially because the problem doesn't even tell you that. But yeah, it's the height of the stick. And what's the kinetic energy translational term? One half mv squared, good. An object that's moving has a, what about the rotational term? One half I omega squared. Good. So now the question is solve for v, right? So we want this thing here. But can we simplify this here on the right? Because I don't want my answer to have the inertia in it. As a matter of fact, I want to use the constraint from A, right, to relate omega to V. I want to say that omega is V over R, right? So I'm going to go ahead and say mgh equals 1/2 mv squared plus 1/2. And now I'm going to write the moment of inertia. So what's the moment of inertia here? So somebody said that I equals 1/2 mr squared omega squared. The I is just the m and the r squared, not the omega term. So it's 1/2 m. And now is this r cylinder or r disk? And tell me why you chose whatever answer you gave me. So remember, here we had RD and RC. Is this RC or RD? Who knows? Somebody's saying disk. Why is that? So I have some conflicting opinions here.
Wouldn't it be the cylinder because that's what's making contact with the ramp?
That's a good argument to make. So somebody says it's a thing rolling. The problem says all the mass is on the disk, right? So remember, technically you have two things, right? So ordinarily you would just say that the moment of inertia is moment of inertia of the one thing plus the moment of inertia of the other thing. However, moment of inertia is, you know, some constant like 1/2 m of one thing times the radius of the one thing squared plus some other constant. Let's say maybe, I think for a cylinder, it's 2/5 mr squared. But the problem states all of the mass is contained in the disk. Somebody wants me to zoom out. The problem states in the third sentence, most of the mass is contained in the disk. So if this is like 1,000 and this is like 0.2, isn't I2 significantly greater than I1? And I is roughly equal to I2? Is everybody okay with that argument? The moment of inertia of the cylinder does not matter. The reason it does not matter is because the mass of the system is contained in the disk. So this is our disk. Luke asks, where are we getting 2/5? That's just the coefficient that goes in front of the moment of inertia of a cylinder. And I think it's 2/5. I'm not even sure. But what I'm, oh, I wrote this backwards. This should be, what I'm trying to say is this is much greater than that, right? So this term is negligible. So now we've defined the moment of inertia, and this should be squared. And now this should be V over R squared. But the question is, once again, is this R the disk or the cylinder? It says the moment of inertia of a disk is 1/2. So do we just put that in for I? Okay, let's backtrack for Jacob and Nick. Somebody said they're saying it says the moment of inertia of the disk is 1/2 mr squared on the page. Do we just put that in for I? Yes, that is exactly what you're gonna do, but you need to understand what is the R? Is the R this or is the that? Now, if your logic is, well, they give us the moment of inertia of one and not the other, so that's the one I'm gonna use. I can't be angry if you use that logic, but I'm guessing that you don't really know why. And the point of this is to tell you why. The reason I'm telling you it doesn't matter is because the moment of inertia is the sum of the two of them. And one of them has a mass much greater than the other. So you can neglect it. Okay. And somebody said the cylinder because that's what's turning. That makes sense. So now that's all there is to it, right? Now you want to solve for V. So you've got mgh equals 1/2 mv squared plus 1/2, erase that there, times, this should be another 1/2 here, by the way, 1/2 times 1/2, that's 1/4, m rd squared times v squared over rc squared. Yeah, Cassie, Arda, I saw that I missed the 1/2. I threw it in here just now. So all I did is now I want to solve for V. So the first thing is I have an m in each term, so I'm going to cancel them out. Oh, I didn't mean to erase, but I guess that works. Actually, I won't do that just because somebody might get confused later. Cross, cross, cross. GH equals 1/2 V squared plus 1/4 RD squared times V squared over RC squared, right? We really want to solve for V, so factor out V. GH 1/2 plus RD squared over RC squared over 4. Divide this on both sides. That cancels and you get V squared equals GH all over, and then you take the square root of both sides. Now in general, I don't bother solving a problem through to the end, but I think some people were confused as to how to do the math here, so I went ahead and did it. Why is there a 2 there? I don't think it's supposed to be a 2 here. Are there any questions about what I did here? Are there any questions as to why we chose one R for one thing and the other R for the other thing?
I understand why you chose it for the disk part, but I'm slightly confused on why you chose it for the cylinder part.
Why this is RC and not RD?
Yeah, exactly.
Yeah, so let's go back to this picture here. There's something that's rolling, right? Like let's say a wheel that's rolling. We say that the velocity of the wheel is going to be the angular velocity of the wheel times the radius of the wheel, right? So that's this radius. And the thing that's making contact with the stick is the cylinder, not the disc. So basically the discs aren't even rotating at all, right? The discs are just hanging out by the sides. And as the thing slides down, it gets churned because the interior is churning, but it doesn't necessarily have to, right? Like if they were independent of each other, then it might not even churn at all. What's really churning is the interior part. So, you know, if we look at this picture, I think there's a better picture. This is what's making contact with this. This is what's churning based on this radius here. Okay. Everybody okay with this?
Can you like go back to where it says V equals W equals and R equals?
Yeah, 1 second. Homework number 9, Q2. V equals, where was that?
Right there. Yeah. Thank you.
Okay, good. So is everybody good with question 1 on the homework since people want to go through 2, 3, and 4? Okay, we'll talk briefly about 1, 2, 3, and 4. Is everybody, can I scroll down here yet?
Yes, thank you.
Okay. So without any questions on this, going once, twice. All right, moving on. Question, so let's do question 1 just for the sake of staying in sequential order. 1 should be relatively quick because we kind of already did it in a previous recitation problem. You have, let me look at the question carefully. You have a homework number 9. You have a child on a swing, and they call this point A. They call this point B. And then they call this here point C. And this angle here is theta. This angle here is phi. Yeah, that's a pretty good picture. They tell you that the length here is L. So obviously this is L and this is L. That's not an L. Okay. The child pulls the swing back to an angle theta and releases it from the position A. However, a strong wind is blowing from left to right, meaning to the right, right? This means that it will swing to a larger angle phi on the right at a position C than it started on the left. A, find the speed of the swing at position B in terms of FW, ML, theta, and G. So who can walk me through how you do that? This is a conservation of energy problem, right? Just like in the spring, there's an energy at the beginning, there's an energy at the end, and there's a work done by a non-conservative force, right? So if we can define 1, 2, and 3, we can say EI plus or minus work equals E final. So what is EI, or energy initial?
Is it potential energy of A?
The potential energy at A, right? Which is given by mg. This is part A for everybody that's on board. I know that there are specific questions about B, but it's easier to just go through the whole problem. So how do we define this potential energy here? Mg times
H, but then you have to figure out
right.
that. It's like trig.
Right. So really, initially you're at a height here, right? And then you're at some height here. So what you really want to find is this distance here. Oh, crap, no. What you really want to find is this shaded part, right? Because initially you were at some, this is like a y1. This is a y2 now, right? Like it's a different height than this. Does that make sense to everybody? Like if we look at the paper from top to down, at A, you're at a higher point than at B, right? So how do we define that? How do we define that length? Well, it's going to be the length from here to here minus the length from here to here, correct? Which is just L minus L cosine theta. Because the length from this point to this point is just L, right? The length of the whole thing. And the point from here to here, using trig, if this is L, then L cosine theta is this part. Is everybody okay with that? Good. I like this color. I'm going to use it more. EI equals mg. Okay, so we've defined E initial. E final is what? Is there any potential energy at B?
No, but there's kinetic.
Good. Which is given by 1/2 mv squared. And actually, I'm going to rewrite this in a way that that is better, in my opinion. I'm going to factor out the L and say 1 minus cosine of theta. And you'll know that it's correct because if you look at this equation, when theta is 0, so like when this thing is 0 and the thing is vertical, you're going to have mgl 1 minus 1 is 0. And what did we just say? When we're at B, there's no gravitational potential energy. And when we're theta is 90, meaning when this is all the way up here, right? Like if it was here, then the gravitational potential energy would be mgl 1 minus cosine of 90, 0, would just be mgl, the height of, this whole height. Okay. What is the work done here then by the wind? Or I think they called it work by wind. It's going to be the force of the wind times what?
Is it distance?
Yes, the distance and along X or Y?
X?
Yep.
Oh, yeah, X.
And how
Then
do
isn't it L sine theta?
and X, right? This length here is defined as L sine theta. So this becomes F of wind times L sine theta times cosine of theta. Actually, let me use a different angle here. This is alpha. This angle is the angle between the force and the displacement. In which direction is the force? To the right. In which direction is my displacement along X? To the right. So what is the angle alpha here? 0. So this is equal to 1. So why did I do that? Why did I unnecessarily add the 1? Well, I want to know if the work done by the wind is positive or negative, right? So mathematically, I can do this, or intuitively, I can say, is the force to the right? Yes. Is the displacement to the right? Yes. So this is plus. Is that okay with everyone? So this is 1. This is 2. And now 3. Oh, wait, we already did 3. So now we just put 1, 2, and 3 together. MGL 1 minus cosine of theta plus force of the wind times L sine theta equals 1/2 NV squared. That's the equation you set up. And then I think the question is, what's the velocity, right? Yeah, find the speed. I'm not going to do that here. You can do that on your own. This is just solve for v, right? You know, multiply 2 on both sides, divide m, take the square root. Now, somebody asked, how did you know to use the x value instead of the y value? Don't forget the fundamental thing here about work. Work is force dotted with displacement, which is force times displacement times cosine of theta. If the wind is to the right and the displacement is down, what's the angle here? 90. So the work done by the wind in the y direction is 0. But the work done by the wind in the x direction is not 0. If you're confused about this, go back and do the first recitation problem for work where we derived the work energy theorem. Okay, if the force is perpendicular to the displacement, the work is 0. Remember the question about the pendulum, right? Why is tension not doing work? Well, tension is always perpendicular to the displacement. Why does the normal force never do work? The normal force is always perpendicular to the displacement. So if work is force times displacement times cosine of theta, if the theta is 0, then the whole thing is 0, okay? So that's why we use the x, because we knew that along y, it wouldn't do any work, but it will along x. So now what everybody was asking about, how do we solve for b? Before I move on, any questions about how we did a? Okay, so for b, it says, write down an equation that you can use to solve for the angle phi in terms of FW, M, L, G, and theta. So what approach do you think we're going to use here? Like what physics intuition are we going to use here? Or what physics concept? In the top right equation. Jessica, where is the -1? I don't see a -1 anywhere.
For the 2 equation, and then in the top right, there's the FWL sign, but then I would think there would be a -1.
Here?
Yeah.
This is not -1, this is +1. Because which
Oh, I see. So you're saying it's equal to 1.
Yeah, this is like an equal sign.
Okay, thank you.
Why is it 1 minus cosine theta? Remember, from here, we want to find out this red part. What is this length? Well, it's going to be this length minus this length. What's the length from this point to this point? Well, that's just L, the length of the string. And what's the distance from this point to this point? It's going to be L cosine theta, right? If you make this triangle, this is the hypotenuse. This is the adjacent side. So now at one point I had asked, what do you think the approach is going to be here? And somebody says kinetic energy at B and potential energy at C. That works. And what I meant to say is we're going to use conservation of energy. We're going to use conservation of energy for quite literally almost everything, right? Now we're going to say this is the initial and this is the final. We could say this is the initial, just like with the spring problem, we had the choice of making this or that the initial. It's completely up to you, but let's use this point B as the initial. In case you haven't caught on, we're going to define these 3 things: energy initial, energy final, and the work done, if there is work to be done, okay? It's the exact same thing that we did with the spring. 1, 2, 3. If there's work and then there's energy, You just define the three things. So EI plus or minus work is going to be equal to E final. Okay. What is the initial energy? Well, we agreed that this is just kinetic energy, right? There's no potential energy at this point. So that's 1/2 and B squared. As we're going from B to C, is the work positive or negative?
Yeah. Positive.
Right?
Positive.
Displacement is to the right, wind is to the right. So this is work equals plus F L sine of phi, right? Does that make sense, everybody? The same way this was L sine theta, this is L sine phi. What's E final? It's a mirror of the other. The only thing is that phi and theta are not equal to each other. So 1, 2, 3, right? 1, 2, 3. You see how there's a pattern here? Like we're just defining 1, 2, 3, 1, 2, 3. 1 plus or minus 2 equals 3. Not more complicated than that. It really isn't. It doesn't matter what the problem is in general. You can solve this using this method. So I've got 1/2 mv squared plus FL sine of phi equals mgl 1 minus sine of phi. That's it. You don't even have to solve this. You just have to set up this equation. That's quite literally it. Oh, sorry. Yeah. That was a mistake, Kaylin. Good call. This should be cosine. My mistake. Thanks for pointing that out.
Why is work in the initial energy? Like, why is not at the final? You said energy initial plus work of the wind equal energy final.
Why is work with the initial and not the final? So the initial energy plus the work provided by the wind is what's going to get us to that final energy.
Oh, okay.
Yeah. Make sense?
Yep.
We know this quantity, the initial is less than the final because we're doing positive work. This number, so yeah, this is another thing to keep in mind, right? So I've said to some of my students, you know, EI, then there's work, and then there's E final. Like if this is 10 and this is 7, this has to be -3, right? But the opposite also works. If this is 10 and this is 7, this has to be +3, right? So this would be a plus or whatever. So what we're trying to say here is if the work is positive, then your initial energy is technically less than your final. And it's only the same when you add the work. If your work is negative, then your initial energy is more than your final energy and you actually have to subtract. Does that make sense, everybody? It's kind of a different way of thinking about it. I've never seen anybody teach this that way, but it's the way that makes sense to me. Like the wind is quite literally helping you go further. So you started with less than what was necessary to get to phi, right? If in the absence of air resistance and all this bullshit, if I start here, I should have ended at a symmetrical angle theta. This is where I really should have ended. But because wind is assisting me, I can go further up. That means that my initial energy was less than my final energy because something helped me out to get to a higher level. If it was the opposite, if I started here and the wind is blowing against me, then my new angle is going to be less than theta, right? It would be something more shallow, like this maybe, because the wind is slowing me down. So my initial is more than my final because something took away from me and I couldn't go as far. Does that make sense, everybody? And that kind of leads us to the next part of the problem. When you go back, are you going to get all the way back to theta? Well, no, it's not going to get us back to theta because now we're going against the wind, right? So in theory, in the absence, now let's say that you turned the wind off. If you turn the wind off, then I should be able to get to this point here, which is really phi, right? But you don't turn the wind off. So I'm actually going to end at a shallower place, right? I'm not even going to get back to theta because the wind, now I'm going left, the wind is going right, it's taken away from me. So if we reverse this process and we call this the initial and we call this the final, my initial energy is more than my final, wind is going to act against my initial energy. Okay. I hope that I'm not blabbering and not making sense, but I think this maybe has reached a few of you. It's non-conservative because it's taking away energy, right? It's taking away energy that you're never going to get back. So for example, like if in the case of a spring, let's say that this is the equilibrium point, right? If the spring is stretched out this way, right? Like let's say here it was moving with some kinetic energy, it stretches all the way up to here and now it stops moving. When it stops moving, the kinetic energy equals 0, right? But shortly after, it's going to recoil and it's going to go to the left. So it's going to regain that kinetic energy. You're always going to be able to take back the energy that you gave up. So when you were this mass going through the equilibrium point, you had your peak velocity. And then you went to the right, slow down, come to a stop, reach maximum potential, leave. Maximum potential, and then you go back to the left, right? Even though you lost kinetic energy going to the right, it was changed into potential energy, which you then got back and converted into kinetic energy again. And that kinetic energy brings you past this equilibrium point and then gets decreased again and becomes potential energy again. And then it goes back and forth, right? And you're always going between kinetic energy and potential energy. If this was friction, friction's going to slow you down and that's it. Friction's not ever going to give you that energy back. That's why it's non-conservative, because nothing gets conserved, right? Like if you're going up a ramp, or not even a ramp, if you're on a flat surface and I push a box, right, to the right, I push it really hard and I let it go, it's going to slide to this point. Friction's going to slow it down and it's going to come to a rest. Friction is never going to accelerate that box again. On the other hand, if there's a ramp, right, and the box is here, and I push it all the way up to here, right? I put some work into making the box go up. I let go of the box, gravity's gonna give me that energy back. Gravity's gonna accelerate the box and move it down. That's a conservative force, right? The work that I put into it doesn't get lost. I'm gonna get it right back one way or another. I hope that helps some people to think about like really the physics, not just the equations going into this stuff. So anyway, let's move on to, I think there was a question about one. Did we want to go over one again? I forgot. Oh, this was one, my mistake. Two, the money question that a lot of people have been confused about. Somebody asked, are we going through all the problems in homework 9 or are we just doing number 1? Yes, we're going over all the problems in the homework problem. Number 2. So again, it's really important that you draw the picture. So let's go ahead and grab a useful color here. So number 2 is homework number 9, Q2. I'm going to try my best to draw a very clear picture here, because if I don't, It might be a little confusing. So let's imagine this is the ceiling. This is the ceiling. Oh yeah, before I move on, are there any questions about one that, again, no silly questions. Are there any questions about what we discussed here? I kind of went on a rant about conservative energy and non-conservative energy, but
I'm just kind of confused on the last question, I guess.
the
Like
last
1C.
1C, yeah. So what's your confusion there?
Like I don't really know. Like I wouldn't think it would just stop at position A. I would think it would like keep going.
Well, the question isn't does it stop, right? The question is, do you make it all the way back to A? Now, would your answer be you do make it back to A or you don't make it back to A?
You do make it back to A.
But what about the fact that now you have to overcome the force of the wind slowing you down?
So does the wind work against it so it doesn't go back to A?
Right, because now you're going from C to A, meaning you're moving to the left, right?
Right.
And the wind is moving in which direction?
Oh,
To the right.
to the right. Yeah.
The work on you is now negative, which is going to take away from that initial energy that you had at point C. So
Okay.
that's why you don't get back to A, because now the work is negative, as opposed to in the beginning when you're going from left to right. Oh, I'm going right. The wind is going right. We're friends. Great. Now you're going against the wind. Now you're enemies. Not so nice.
Okay. Thank you so much.
No problem. Somebody said, can you do B? I'm assuming you mean B for question 2, right? Or did you mean to go over? Okay, yeah, don't worry. We're going to get to all the parts of each problem. So the first thing I did is I drew a picture and I said, okay, cool. So at first we have a spring and it's just hanging out from the ceiling. And this line that I'm going to draw in, what's the most annoying color that I have? It's not annoying, but it'll stand out. This here is what I call the equilibrium position. So if I have the spring and it's just hanging out, right? That's the equilibrium position of the spring. At this point, the spring has no potential energy, none whatsoever. There's no potential energy in the spring. That's what it means to be at equilibrium. Are we all in agreement with that?
So when the spring isn't stretched or compressed, it's at equilibrium?
Correct.
Okay, thank you.
Yeah. So the spring is just hanging out. And in part A, you attach, let me actually write this lower down so it doesn't interfere with my pictures. You attach a 1 kilogram mass to the spring. Where does it settle? Wow, I love how my handwriting changed so much there. So there's a disclaimer here that's a little subtle that I'm going to make because it's not obvious. You cannot use conservation of energy here. The reason you can't use conservation of energy here is because energy is not conserved in this process. And we don't really have a way of talking about the work done, because what's going to happen is when you put a mass here, it's going to go down. But then because of the fact that the spring has some potential energy, when it's stretched out, it's going to go back up. But then there's gravitational energy, so it's going to go back down and stretch out the spring. Then it's going to go back up because the spring's been stretched. But then there's gravitational potential energy, so it comes back down. So realistically, the spring should be between, not like that, let's see, between these two states continuously. That's what you would call a simple harmonic oscillator, meaning you go from A to B, from A to B, because here I have gravitational potential energy, here I have spring potential energy. So I go back up, now I have spring potential, now I have gravitational potential energy again. So it goes back and forth. However, this problem is saying that it settles at a specific height, meaning that eventually this oscillation was damped out and it stopped, right? So we can't use conservation of energy here. But we can still think about this problem in a way that's kind of obvious. So in scenario A, right? I mean, I don't know about obvious, but you have the tools for it. I've attached a 1 kilogram mass, right? And it moved a distance, let's call it y1, right? It moved a distance y1. And we want to find out what that distance is. How do we solve this here? Well, I would use forces. I would say, okay, well, I have a mass that's just hanging there. I know that it's a spring, so I know the force due to Hooke's law is minus kx. And I know that if I draw a free body diagram on this box, I got mg and I got Hooke's law, right? And the acceleration along y is 0 if it's not moving. So then F right? They're equal to each other. Hadar, the quiz tomorrow will be like the last quiz. So I think it's 1 hour, 2 questions. Oh, I think you had 3 questions last time, but I think you're only getting 2 questions this time. Don't hold my feet to that. But yeah, I think it's 2. So now we just want to solve for x. So let's actually call this y1, right? Because that's how much it was stretched. So y1 is mg over k, which is 0.1 meters. Because, you know, the mass is 1 kilogram times 10 meters per second squared. And the spring constant is 100, sorry. So it goes down 0.1 meters.
Does it say AV equals 0 or AY? I'm confused.
AY equals, so the acceleration in the y direction of this thing is 0, right? Because when it's just hanging out here, it's not accelerating anymore. So if I draw a free body diagram on this thing, I just have the force of the spring, right? And the force of gravity. And if it's not moving, they have to be equal to each other, because if we do the sum of the forces, F spring minus Fg equals MAY, which is equal to 0. So F of spring equals F of gravity. F of spring is minus KY1, which is equal to mg.
Okay, thank you.
Okay, good. Kelly, I'm glad that you found that simple. Yeah, the part A is really just that simple. Okay. I'm actually going to erase this because I'm going to need this space. Actually, I won't erase it. I'll move it over to here. And then I'll say y1 equals 0.1 meters. Cool. So now I'm actually gonna go ahead and draw B up here. For B, we attach a second mass. Of 1 kilogram. So I'm gonna draw the picture of here. Is K not negative anymore? Yeah, so the K is negative, But so is your displacement, right? Because you're going from a higher to a lower displacement, so those negative signs cancel out. The G is in fact non-negative here because I accounted for that when I said Fs minus Fg. But this is minus K, and then if we're looking at delta Y or whatever, that delta is negative. So now we attach a second mass. So now the spring is gonna do the following. Let me actually shift all of this down just a little bit. The beauty of note-taking on an app. So now we're gonna attach a second mass. So now it's 2 kilograms, right? And it went an extra distance, which we can now call Y2. And of course, from equilibrium to the new height, no, okay. This here would be Y1 plus Y2, right? This is the distance from here to here, and from here to here is Y2. So from the original equilibrium position, it's Y1 plus Y2. Do we agree with that? Kelly agrees with me. Does anybody else agree with that? Okay, good. So now what we want to find out is we don't want to find out where it settles. We want to find out what's the lowest it'll go. So how low can you go? How low is the maximum displacement of the mass? Now, the reason we phrase it that way is because remember, eventually it's going to go back and forth, up and down, and it's going to settle at some height, right? And don't worry, that's part B. But what we want to do is we want to say, okay, well, here I added a mass, so it went down and up and down and up and down and up and down and up. And eventually it settled, probably somewhere here. Not the highest point, but not the lowest point either, right? So it probably settled somewhere here. And I'll leave that, I'll make that a better picture later on. But now the beauty of this is that now we can use conservation of energy. Now we can say, well, if we don't have to worry about the fact that this thing is going to damp itself to rest, then we can use conservation of energy because we're only looking at the time frame between this point to this point. So hey, let's do what we've been doing. E initial plus or minus work equals E final. There is no external force that we're considering in this part, so this is 0. So we're doing, 1, 2, 3, 2 equals 0. What is E initial? Well, E initial is when the mass is here, right? But it's 2 kilograms. When the mass is here, but it's 2 kilograms instead of 1. You put on the 2 kilogram mass, and then when we let go, it's going to come down here, back up, here, back up, and then it's going to settle to this point. What is the energy? Is there any kinetic energy when we're here? No. So if we say the initial energy is the kinetic energy, initial, plus the potential energy of gravity initial, plus the potential energy of spring initial, this is 0. Is there gravitational potential energy here? Yes. Of course, because you're gonna put, you know, a mass on it and it's gonna go down. Gravity's acting on it, so there's gravitational potential energy. And that gravitational potential energy, well, that's gonna be mgh, right? Where h is what? The distance from here to here, which we called y2. So that checks out. And we're gonna say EI is equal to mg, and it's actually 2m, right? Because we added a 2 kilogram mass. Let's just call it m, and then we'll plug in what m is later. Y2. We agree with that, right? Does the fact that I call this distance y2 for mgh make sense, everybody? We're going from a height of here to here, and that distance is y2. Is there spring potential energy here?
Yes.
Yes. And what is it? Oh, somebody said no. Why? What is the argument for there not being spring potential energy?
Well, I just figured because like even though it's not at like the equilibrium point, it kind of settled.
Kelly's right? If you are away from equilibrium, there is a stretch or a compression, meaning there is spring potential energy.
Okay.
And that's why I drew this so carefully like this, because I wanted you to see that when you're here, you're not here. And if you're not here, there is spring potential energy. Okay. So yeah, it's settled, but that's only because we used a force to bring it down. So plus 1/2 K, and then what is it? What is the delta here? Is it y1 or y2? Or is it both? Somebody's saying it's y1 plus y2. Why do you say it's y1 plus y2?
Because that's the total distance you moved away from the starting point.
But you haven't moved this distance yet. You're still here.
Oh, so it's just y1.
It would be y1, right? It's how much there is in the spring at the moment. At the moment, I am a distance y1 away from equilibrium. So my spring potential energy is 1/2 K y1 squared.
So it's based on the initial position?
For the spring, yes, because the initial energy, right? For the spring, it's the initial energy.
Oh, right, yeah, okay.
Y2, because when we're talking about gravitational potential energy, is we're talking about what distance can gravity do work over, right? It's not what work gravity has already done. Does that make sense?
Yeah. Is the spring energy negative because it's like opposing motion or no?
No, because this number here is always going to get squared. So whether it's negative or positive, you're always going to get a positive term out of it.
Okay, gotcha. So like the spring energy is just always positive.
Right.
Okay.
And now work. So this is 1. Cool. 1 meaning, you know, I hope this labeling helps you guys, help you follow. Okay, this is the one thing we need to figure out. This is the next thing we need to figure out. Oh, we already did. So we've got 1 checked off. We've got 2 checked off. And 3. EF. How do we define EF? Is there spring potential energy? I mean, is there a gravitational potential energy when you're here? Half and half.
I think no, because we set that as our bottom, but I'm not entirely sure.
Jacob is exactly right. So the people that said yes, you're not wrong. However, it would be wise of you to change your frame of reference. You know, you can make this your y all the way down here. You can make this your y equals 0. But it would be smart if you make this point your y equals 0. Because if you make that point your y equals 0, then gravitational potential energy is 0 at that point. Does that make sense, everybody? So again, it's not that you're wrong if you said that there was gravitational potential energy, because you are free to choose your floor. I'm saying it would be smart to make your floor this height here so that there is no final gravitational potential energy. Does everybody click with that? So is there any kinetic energy at the bottom? No, right? Because that's when it's going to stop and then go back up. But there is spring potential energy, right? And how much is that? Exactly. Now it's how much you actually stretch the spring away from equilibrium, right? So if this is equilibrium, it's this whole stretch, which is y1 plus y2. So you would say E final is 1/2 k y1 plus y2 squared. You know, you're free to call this y3 or some other variable, so you're not adding two things, but I called it y1 plus y2 so that you can see where it comes from, right? And that's why I went out of my way to make this picture so clear to the best of my limited abilities here. So, you know, now the rest of the game is just 1 equals 3, right? 1 equals 3 because there's no 2. So mg y2 plus 1/2 k y1 squared equals 1/2 k y1 plus y2 squared. Pretty simple, maybe? Maybe not. This is kind of ugly to solve, right? I think, do you even have to solve it? I think you do. Yeah, well, I'm not going to solve it. You can solve it. You have all the numbers here. But it's a quadratic equation again, right? You have this x squared term, you have this, and you have that. It's pretty ugly. And yeah, for the m, it's 2 kilograms. For the m, it's 2 kilograms. And Kendra, no, it is not the resting point. Correct. This is the furthest point it will go. So now let's talk about the resting point. Well, the resting point, it's the same thing as here, right? You say, okay, well, this thing has been displaced some distance, right? And it's hanging out here. So what's the forces acting on it? Well, there's the force of the spring. There's the force of gravity. And because we're no longer moving AY 0, so the force of the spring is equal to the force of gravity. So I have minus kx, or, you know, y, which is what we're solving for, equals, and this is also a minus, so it's a plus, equals 2 times g. And then, you know, y is 2g over k. So A and C are pretty simple. 2 is a little bit more nuanced and kind of gross when you have to solve for it. But again, you know, I don't expect the Walter is going to give something that's hard to solve mathematically, because he's not testing to see if you know how to solve a quick quadratic equation here. He's just testing to see what do you call it? What if you can even get to this point. Somebody said, are we solving for y1 plus y2? Well, we know y1, right? We solved for y1. We know that this is 0.1. So you could plug that in there. What did Fs mean? That was the force of the spring, right? The spring pulls up on the mass, gravity pulls down on the mass. They're going to be equal and opposite forces when the mass is at rest.
I have a quick question too. For part B, where you wrote the equation for EF, where did the 1/2 come from? Like, I get the K and the Y plus 1 plus Y2 part.
Where did the 1/2 come from? Well, it's the spring potential energy, right? The spring potential energy is always 1/2 K, and then the change in position squared.
Oh, sorry, I was thinking of the negative kx.
Yeah, so the force of a spring, oops, so force of spring is minus kx. The potential energy of a spring is actually the integral of the force. Which is 0 to x minus kx dx. This is minus kx squared over 2, evaluated at x and at 0. So P, let me zoom out a bit. P and the minus sign cancels because you had to divide by the, wait, does the minus sign cancel here? Hold up. How did I get rid of the minus sign here? There's a factor of -1 that I'm forgetting here. Have minus k, that's just a constant. Yeah, I don't remember how you get rid of the minus sign here. But the point is that the force of the spring is minus kx. The potential energy of the spring is positive 1/2 kx.
Okay, thank you.
Yeah, I mean, you can switch x and 0, but why would you do that, right? Yeah, if you'd make this x to 0, then yeah, you get rid of the minus sign. But why would you do that? Because you're going from x to 0. That doesn't make sense to me. I mean, or mathematically, yeah, that'll give you a positive sign because that, flips this. Yeah, flipping, yeah. So when he did this, he did x to 0. Okay, yeah. So I just don't remember why it's x to 0 and not 0 to x. I mean, I know the math-wise, yes, if you flip the balance of integration, you flip the sign here because, you just flip in the order of the addition, of the subtraction. But physically speaking, there should be a reason as to why you're going from x to 0 and not 0 to x. But that's not really that important for you. What's important is that you know this equation and this equation. Okay, so we've answered number 2. I think everybody that's been actively talking is on the same page as me for 2. Are there any questions? Somebody said, so for B, if we get delta x, should we add that answer for A? Oh, well, it really depends on your notation here. I mean, if you combine this into one variable and call this like y3, then you've already added the 0.1. If you solve for this differently, you kind of FOIL this out, then you don't have to because you've already added the 0.1 plus some unknown distance. Okay, any other, I think I'm gonna start zooming in because the work comes out a little bit more clear. Question.
Can I ask a specific question about question 3?
Yeah.
Something like super specific in part B. The work that is done, so it's going from up to down. So the bicycle is, he's up on the mountain and then he exerts work. Will the work done by the gravity be positive or negative at this position when he's up there?
Good question. Very good question. So this is Alice, yeah. So this thing is 500 meters long, right? And you're saying for part B, when you're up, you've got some initial gravitational potential energy, mg 500, this is 30, so it's sine of 30. and E final is 1/2 NV squared, right? Where we know V is 30, I mean 13. So this
Is it 0 at the final stage?
is what 0? The velocity?
The velocity?
No, they wanna go downhill, right? And they want to travel up to 13 meters per second. So they start with no potential, only potential energy, and end up with kinetic energy only at the bottom.
Okay.
Because if your velocity is 0, you're implying you're stopping here, which why would you?
Okay, so initially it's only potential.
Initially, it's only potential because you're at rest here. Your final is, well, when you're down here, there's no more gravity. But then there is the work done by something, right? And that's what your question was about. Work done by what?
Bicycle, the person itself.
Brakes. That's how you spell brake. Brakes. So 1 plus or minus 2 equals 3, right? That's what we've been doing this whole time. So we've got mg, I'm just going to call it h because it's more clean to write, plus or minus the work done equals 1/2 NV squared. So your question is the work done positive or negative, right? Is that what you said?
Yeah.
Well, what is your guess before I answer you?
No, I guess I set it up very differently. I didn't set up like you. It seems like it's negative work here.
It would be negative work, right? Because if this is one of the cases where I have E1, E initial, and E final, and my E initial is greater than my E final, so I need to subtract the work, right? And,
Yeah.
and we know that it's greater because if we plug this in, sine of 30 is, I think, 1/2. So this is 75 times 10 times 1/2.
So in this case, when you do the energy before equals energy after, I mean, you're actually doing energy before plus the work done equals energy after. So is this like the total energy and the work is by non-conservative forces? Because this is something confuses me. Because this is a work that's done by something that's not gravity, right? Or that's something that's not the spring. Like obviously there's no spring here, but like, I mean, I'm saying non-conservative.
Exactly, it is not conservative. And think back to what I was saying earlier. The work that the brakes do to slow you down, you're never getting that work back, right? You're never getting that work back. So it is non-conservative, which is what we just call it minus W. If it was conservative, it would actually be a source of potential energy. That's one way of thinking of this. If the work done by a force is conservative, then that force is a source of potential energy, like gravity and springs. If the force is non-conservative, then we just say it does some work. We never got that work back.
Okay, so non-conservative, we just put it like work, and the spring and the the gravity, we can just put it like this, mg, and okay.
Right.
Thank you.
But yeah, this you said you did a different. What was your approach to solving for the work then?
Yeah, so I said also the work done by gravity, and it's the same thing as mg, but it confused me. Like I did work done by brakes plus work done by gravity. Never mind. I think this is much better.
Remember, the work done by gravity and the gravitational potential energy are similar, right? Because the work done by gravity is the same as the gravitational potential energy. So you would kind of be right if you did that. I do think this is a little more clean and it's easier to follow sequential steps, but you wouldn't be wrong to say that the work done by gravity. You can't think of it in terms of the work done by a force, whether that force is conservative or not. But I think thinking of it in terms of kinetic potential energy is easier. In my opinion, of course, not the law or anything like that. If you come to the same conclusion here, then you're good. But yeah, what I would do is I would say, well, there's some energy at the beginning. It's only gravitational potential. There's some energy at the end. It's only kinetic. I need to do some work to slow it down. Okay.
Okay. Yeah, thank you. And about that question from the recitation, I know you won't get time to answer that, but could I ask you it afterwards on email or something? It's just that question 3 from the recitation.
Yeah, it's already in. We can actually do that. What's question 4?
I know people had also questions from that. And I don't want to, I know you said it's less important, so.
We can do question 3 from the recitation after we finish this number 3, and then we'll do 4. But
Okay,
wait,
I do have a meeting that I have to go, so sorry, but I will be back if I can.
just email me your question in particular, if anything, and I'll try to respond to you before tomorrow morning.
Yeah, that will be better. Thank you so much. Thank you.
No problem. Kelly, wait, hold on. Let me scroll up. Okay. Leonardo, Leo, I'll address your question later, but yes, that's fine with me. Luke says, can you scroll up to part C and 2? Oh, I think I wrote it here. Somebody said, where did the 110 come from? Oh, sorry, that should have been a 1/2, my mistake. Sine of 30 is 1/2, I think. So I meant to write sine of 30, yeah. And then Kelly said she was confused. So let's actually address question 3 from the beginning. Question 3A says that there's a person going uphill, and the person is a box with, and she is generating a power that is 150 watts. What velocity is she moving with? Right? So power is just work done over time, right? And work is just force times displacement over time. This is velocity. So power is force times velocity. Does that equation make sense to everybody? So now if we want to find the velocity, then what's the power divided by the force that she's applying? That's going to be V. So the power is easy. We know that that's 150, but what about the force? How do we find out the force that a person going uphill like this has to apply to move at a constant velocity? So the person's here. What are the forces acting on the person? Well, there's the normal force, cool. There's gravity. What else? What kind of friction, Kelly? Right, or more specifically, traction, right? Which is a type of static. She's actually on a bike, but force of traction, which is going up, right? So if we break this down, right, into X and Y, then the forces along X are the X component of gravity and the force of traction. So if we do the sum of the forces along X, it's force of traction minus mg sine theta equals max. But we know she's moving with a constant velocity, right? So this is actually just 0. So the force of traction, aka the force that's propelling her upwards, is just mg sine of theta. And well, that's just 70 times 10 times 1/2. So 150 over 75 times 10 times a 2 here. That's the velocity that she's moving with. That's how you do it.
I have a question.
Yeah.
When do you know when to use sine or cosine for these problems?
So good question, actually. We know that this is 30 degrees, right? Or this is theta rather, which is happens to be 30. Actually, I think I wrote a picture earlier. Yes. Look at this picture here. This angle is theta, right? Which means this angle must be, we know that this is 90 degrees. So this angle must be 90 minus theta, right? Because this has to add up to 180. If this is 90, and this is, let's say, 30, this must be 90 minus 30, which is 60, right? This is a 90, 30, 60 triangle. Does that make sense?
Yeah.
So I know that if this side is 90, this side is 30, this must be 60. However, if you look closely here, what's the angle made here? Between the ramp and my new y-axis when I rotate my frame. What is the angle here between the green lines? 90, right? It's 90 degrees. But this is 60, so what must this angle be? Must be 30. Does that make sense to everybody here?
Yeah.
So now the question is, why are we using sine instead of cosine, right? Well, this is mg, right? This is mg. And this is my new y-axis. I mean x-axis. And this is my new, my new y. And my new x. So if I wanted to find the component of gravity along my x, isn't it this part? The part parallel to the x-axis? How do I get that length of the triangle? This is just ABC, right? A squared plus B squared equals C squared. I know one of the sides and I know one of the angles. How do I get A or B? What's sine of 30 degrees? It's going to be opposite over hypotenuse, right? Opposite is the A side. A over mg. So A is mg sine of 30. That's where that comes from.
Okay. Thank you.
No problem. And if you wanted to know the vertical component of gravity, how is it 30 degrees? Well, that's what I just erased. Let's go back. Actually, I'll just erase everything here and write it again. Okay. What is this angle here? For Cassie and Cherry. What is this angle here from between these two lines? 90. Oops. What is this angle here? Well, clearly it's 30, correct? I wrote that. What must this angle be? No, somebody had asked me where we got the mg sine theta from. And I said, this must be 30. Now, what must this angle be? I mean, sorry, this must be 60, not 30. So what must this angle be? Must be 30, right? Because this and this make a right triangle, which makes this angle 90. And this line bisects the whole thing, meaning this must be 30. Because 30 plus 60 gives you 90. Cassie, does that make sense? It'll be posted on YouTube. Is everybody that's confused about this okay with this? This may not necessarily be on your test tomorrow, but it's pretty important that you do this. But I'm gonna move on because there are other people that have questions about the last problem of the recitation. So I'm gonna try to get to that. And then, you know, if you still have questions about this, we probably don't have time to address it before tomorrow, but we should at some point. Okay, oh no, the last bit, the home stretch. I know it's been over 2 hours. So for those of you that have been here, pat yourself on the back. I almost don't even want to solve this problem because I'm disgusted with it. But okay, you have this picture here. This is big H. This is little h. There's a ball here, or a sphere rather. Question A. How fast is the ball traveling when it reaches the edge of the table? What do we think we're going to use here? Conservation of energy. Bye, Bridget. Thanks for coming. Conservation of energy, right? So E initial equals E final because work is 0. And the problem tells you that. So E initial, well, it's not moving yet, so it's just mgh. E final, once it gets to here, it's just the two kinetic energy terms, just like the recitation problem. V squared plus 1/2 I omega squared. So then you do mgh equals 1/2, it should be an m here, and v squared plus 1/2 times 2/5 mr squared times v over r squared. Right? This is the same kind of math that we did for the first recitation problem. But in this case, the r's are the same. So this r cancels with this r, and you've got mgh equals 1/2 mv squared plus 2 over 1/5 mv squared. Solve for v. Why is w equal to 0? Friction doesn't ever do work on a rolling object. Because the contact point is constantly changing. The contact point between the cylinder, the rolling, I think here it's a sphere, and friction, it's always changing. So it's not like it's making contact with one place and then applying a force over some distance. That contact is always changing. So you say that the force of friction never does work. So, you know, this is just solve for V. This is really simple, right? You get GH equals 7/10 V squared. Oops. Does that make sense? Yeah, V squared. Solve for V. Yes, the problem will say, yeah, it will say that it's rolling without slipping. Yeah, definitely. So B says, what is how fast is the ball traveling when it strikes the floor? Well, it's the same idea, right? You have E initial, E final, except your new initial is going to be your 1/2 K V, you know, this V, we're going to call it V2 maybe. Should be an M, not a K, burning out here. 2 squared plus the rotational kinetic energy term equals, plus mg and big H, right? Because you're here. 1/2 mv3 squared plus 1/2 I omega 3 squared plus 0, right? That term is. Now the question is, between this point and the floor, does the rotational kinetic energy change? No, it doesn't, right? Because there's nothing to cause it to rotate. So omega 2 and omega 3 are the same. So it's actually just omega 2. So when I equate them, what I'm saying is I have 1/2 mv2 squared plus 1/2 I omega 2 squared equals cancels, oh, plus mg capital H plus that, right? So then I've got mg capital H plus 1/2 nv squared equals 1/2 nv3 squared. Pretty simple. Now solve for v3. Any questions about what we did so far? Can I see the diagram again? I mean, I didn't draw a very good diagram, but you can look up the question. Sodi Cherry, look up the question on Walter's page. His picture is better than the crap that I drew. The H comes from the fact that once we're here, you're gonna fall off the table, right? So you have some gravitational potential energy from when you fall. What is omega 2? Well, that's the angular velocity when you're down here, when you go from here to here. And v3, that's the speed you're gonna have when you hit the floor. Now, lastly, how far does the ball land? Who knows how to do that part? It's actually pretty simple, but there was a similar problem to this in quiz 4 and almost nobody got it right. How do we solve how far the ball travels? It's kinematics, right? X and Y. X final equals X initial plus V X initial times T plus 1/2 AT squared. We know this term is 0. We can choose X not to be 0. No, Jake, in part 2, you're solving for V3. V2 is what you got in part A. Yeah, Rebecca, X of T equation, but you also want to do Y of T. Because now what you're going to say is X final is going to be, well, you solved for V3 here, right? Oops. Sorry, V2, right? Because that's the initial, oh no, sorry, V3. Wait, hold up. Oh, we want to find out from here to the floor. Yeah, so this is going to be V2 times T, where V2 is solved for here, right? And Y, well, the final height is 0. The initial is H minus 1/2 GT squared, right? We have T here and T here. I would say solve here for T. To H over G, square roots. Plug that into there. So X final is going to be this V here, which, you know, let's just solve for V2 is the square root of 10 GH over 7. So it's square root of 10 GH over 7 times the square root of 2h over g. And there you go. Sorry, this should be, yeah, this is little h and this is big H. All right, so at this point, I'm pretty burnt out. Yeah, Kelly, I feel you on that. Can I see Q3 quick? Oh, here? I thought this was Q3. Yeah, I'm pretty burnt out. So, I mean, I can take some questions, but I'm pretty much short of running out of fumes here. But hopefully this was helpful. Do your best tomorrow. I know that I'm a harsh grader sometimes, so I feel bad for the students that I grade. I'll upload this on YouTube right now. It's just, it takes a while because I have to download the thing and then upload it to YouTube. And then once that happens, it'll be accessible on the YouTube page. Yeah, thank you everybody for coming. I hope that was helpful. Have a very enjoyable Wednesday night. And if you're a football fan, enjoy the draft tomorrow. It's the one good thing about tomorrow. Bye. Oh, sorry, somebody had a question. Can you show 4C again? Again, this will go on YouTube, so you can look at this in about probably 30 minutes to an hour or so. Have a good one, guys.
Will this be on like the physics